write down. So for the first one, we have to sketch a vector field. You all eventually figured out that this vector only had a k component, no I or j. So the I and j are always 0, and then you're just plugging your points in to find your k value. So that means that all of your vectors are going to be pointing either straight up or straight down, and when you're limited from 0 to 2 for x and y, all of your vectors end up pointing straight down. That was mine, just drawing a bunch. I just drew a bunch, but they're all pointing straight down. So all of you guys kind of picked up on that, so that was very good. I'm very pleased. All right. Finding a potential function. Well, with the typos now, I'm not sure that my potential functions are correct. We'll see how they go. So I had 3x squared. Let's see.
Yep.
It's right. I just typed it wrong. Okay. Okay. Do we need to go through it, or does everyone? I would be happy to go through it. All right. So, and I'm going to do it using the method that we kind of all settled on as the happier method yesterday. Yes. Yeah. So when you integrate your first part, so let's see. I never know how to write that properly. We'll just do, how about this? Let's just do the integral of 6xy minus 2x. We'll integrate that dx. So you end up with 3x squared y minus x squared, right? And then if you integrate the second part, 3x squared dy, you just get 3x squared y, right? So your potential function, you just write the repeats once. So it would be 3x squared y minus x squared y. Right? Okay. All right. Second one. Hopefully no issues with the second one. xy squared z cubed. Xy squared z cubed. Yes. 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 It's way over. Yeah, good. Good. Good, okay. And I said just find a potential function, so I guess technically you don't have to have the k. That's fine. And then the last one, if we do the integral of negative y sine x plus 3x squared dx, all right, so we get positive y cosine x plus x cubed. And then for the other part, dy, so here we get y cosine x minus y, right? So what do you end up? You have an overlap. The y cosine x gets written one time, plus x cubed minus y plus k. So you end up with that. So, good. Yeah. You guys, did you guys just, oh, you put it up there. Okay. Yeah. Good. 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 Oops. What happened? Just add a vote. Yeah. Okay. That's all right. See? That's how we. Good. All right. We learned from our mistakes. Okay. All right. Today we are going to do 16-2 line integrals. We are not going to finish this today. I can almost guarantee there is no way we are finishing this lesson in the next, well, you never know. We have 55 minutes. I just don't want to rush it because this is kind of important, right? So we'll see what we get through, and if we have to push to Monday, then we push to Monday.
Peace.
The word piecewise should not strike fear, right?
I just never I never mastered that.
Oh my goodness. Also, my nose is moving.
I think I've never used that.
Oh, we're not converting absolute value to piecewise. We're just taking a function and breaking it into chunks. That's all. That's all.
I just never mastered piecewise function. It's such a simple concept, but I've never.
You probably know it better than you. All right. Wow, we're very antsy today. Are we good?
Yeah.
All right. Okay. So, a property of gravitational fields is that if certain conditions are met, the work done by gravity on an object moving between 2 points in the field is independent of the path taken by the object. One of the conditions required for this to be true is that the path has to be piecewise smooth. So we're going to just remember what smooth, we learned what smooth means back in chapter 13. So in case you've forgotten, smooth means that all of your derivatives are continuous and they don't all equal 0 at the same time, right? I don't know if that rings a bell, but we want all of our derivatives to exist and to not equal 0 at the same time. So what ends up happening for our curves for what we're doing today is sometimes they have what we used to call a sharp turn or a cusp. Sometimes that happens. Then, so if there are specific spots where the curve is not smooth, we can still do what we need to do. We just have to break it up into piecewise components, right? So that we have this part that's smooth, plus this part that's smooth, plus this part that's smooth, and we just add them together. So if a curve is piecewise smooth on an interval, if it can be broken into a finite number of subintervals on which the curve is smooth. So, all right. So we're going to talk about piecewise smooth for a minute. Now, part of what you have to do today is write a function in parametric form. Now, we did this in chapter 13. We did it a little in chapter 12. We did it in chapter 13. We had some ups and downs, but we're going to rock this in this unit, right? Yes, I know. Okay, it's all coming back now, right? Okay. So it's okay. Yes. Yes. Okay, we don't have to talk about that. Yes. Okay. Okay. All right, I just delayed it. That's all. Right? I didn't eliminate, I just pushed it off a little bit. Okay, so the easiest way to write a line in parametric form is to actually write the line in parametric form. You all have written linear equations in parametric form, so we don't need to learn any new techniques. We just find our direction vector, use a point on the line, and write your set of parametric equations for the line, right? So there's nothing new here. You've been doing this since chapter 12. So when you're writing a line, if you have to convert a line to parametric form, just do it the way that you've always done. Like if I said, hey, write the equation of this line, and it was in 3 space, right? You would do it. You'd find the direction vector, you'd use a point, and you'd write your 3 parametric equations, right? So what I'd like you to do is take a minute. We'll talk about that in a minute, but just see if you can find the equations for those 3 lines. And we'll talk about like limiting the t values, but first just generically, find the equations of those 3 lines. Find the direction vector, find a point on the line, and write your parametric equations for each of those 3 lines. So take a minute in your groups and see what you can do. All right, so for the first one, I used a direction vector of 0, 4, 0. I took, remember a direction vector doesn't have, like the magnitude doesn't matter. You can do a scalar multiple of it, right? So I turned the 0, 4, 0 into a 0, 1, 0 just to make life easier, right? You don't have to. So Yeah, it actually ends up being a lot
I'm
easier.
like that.
Because we're going to have to restrict our t's pretty soon, right? Okay, so I got an x of t of 0, y of t, and a z of t of 0. Now, what you need then is for these, is you're going to have to restrict your t's so that when you plug in this number for t, you get your starting point, and when you plug in this number for t, you land at your ending point, right? So whatever you got for your equations, you're going to have to find a starting and ending t value that you can plug in and get those points. Now, if you did things backwards, then we have to figure out how to reverse the order. But for these, I tried to write them so that it should be pretty straightforward. Now, you might end up having some fractions if you used 4 as your slope instead of 1 as your slope. That's okay, fractions are fine. Fractions are our friends, right? Yes?
So can you remember how you would do it with the y then? Like the...
Yeah, so if I had, an easy way to do it is just say, so suppose I had my y equals 4t, right? And I want to know what t value gives me a y of 4. Just set it equal to 4. And, oh, you guys don't have any fractions. You just have t equals 1. You just go to 0 to 1. Mm-hmm. Yeah. All right, so I want you to, oh, yes, Sophie.
So I did it with the point 0 for 0. So
Uh-huh.
y equals 4 plus 4t, where t would just equal 0. So then what would the starting be?
All right, so then you would have a 4
Would it be like a
t
negative?
plus 4, and you want that to equal 0, so your t would be -1. You'd be going -1 to 0. That's okay. Still low to high, right?
Can you just like backtrack a little? I just got a little lost.
Sure.
So how did you? Are we talking about like the interval for the t?
Yes.
Okay.
So, if my equation, and I'm just so you know, we're going to get into naming these with like calling them c's with subscripts. But anyway, so if my c sub 1, my vector equation for that line is 0, t, 0, then when I plug in my, like when I have my little restriction here, domain restriction on my t, if I plug in this value for t, I should get my starting point. And if I plug in this value for t, I should get my ending, my terminal point, right? Yes, Jeff?
So if we catch the vector as 0, 4, 0,
Uh-huh.
then the y would be 4t, and then it would be t from 0 to 1.
Yes, it would. Good. All right, did you all figure out your C sub 2 now with your
Oh no.
domain restriction? Okay. For your second one or your first? All right, let's take a look here. So you want to start at 0.040, so you're starting at 0. Yes, 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 yes. Yep. You're okay. You were fine. Yes. 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 I'll do that. I'll be 1 second. Why would you use a negative? Why do you have a negative direction? Remember that your direction vector, you always do ending minus starting, not starting minus ending. Right? That's okay. Okay. I don't know. You have
So 0.07 and then the next one.
Oh yeah.
So, t is greater than 0 and less than 2. Yeah.
Alright, so you have your 3 equations, right? So
I don't know.
Yeah, I understand different now. But yeah, you could have
So I did X.
Oh, I think we do that later though.
I'm just thinking if you figure it out for one,
That makes sense. And then you just put the T in the middle.
like it were
Okay.
Okay, this is your first one, right?
And then I got 0 to 1 last week. But I've had no
So I guess my initial
So yeah, I think this one would be right where this one had like half of it is just like constant for all of them.
Yes, because when you do the two, there are limits to their so once you value is 0.0.
No. But I had force unfortunately. Probably
That one would be the same.
yeah, I also had that as C, but X because like Z is like so and then X equivalent T, Y is
Okay, then one.
there's a way it can ask us to make it sequential.
Yes.
Right. And that's what gives us
Oh.
yeah.
because
Okay.
I thought
Okay.
the boundaries still
Where's, is this your second? Okay.
zero is
Okay. So your condition is 0, yeah.
because
My first two are equal, then I would have 0.
Yeah, that's right. Okay, and
And
then
that's not that bad.
so this is your vector. Or is that y squared equals 10. So your starting rate is 2 or 0. That's right. Good. Rejoice. Got it. Okay? All right. So as we have learned, there are different answers depending on how you wrote your direction vectors. So we'll do more of this. Don't worry. We're going to do it in the context of problems, though. But it's, wow, it's good that we had a refresher. Obviously, we needed one, right? Okay. So a little note, because we're going to be converting a lot to parametric form. If your equation is something like, if you think of it, if you have an integral where you would like typically in last chapter like write in polar form, then you might want to go with x equals r cosine t, y equals r sine t instead of just a t kind of a thing, right? It tends to work out nicely if you kind of think of them as a polar conversion. If you had an integral that you would have normally done in polar form, yes.
Are we gonna sequentialize the t-values?
So, good question. So the question was, do the t-values have to go like 0 to 4 and then 4 to something and then something to something else? They don't have to be sequential. You can, as long as the t's are correct and produce the correct curve, you'll be fine. Yeah, good question. Jack.
So if you don't change the original direction vector, does it always t from 0 to 1? It was that in this case, right?
For these,
Yeah.
not always. 0 to 1 gets used a lot, but it's not, don't count on that being like a given. Okay, the other thing to remember that I wrote here is most of the time you're going to be parameterizing in two space, because most of it, these will be regions enclosed by curves like on a plane, and you'll be using that to do stuff with a z above or whatever like we've been doing before. So most of the time you're going to be parameterizing in two space. So if you're ever stuck, you can just let one of the variables be t and just plug it in for the other variable, right? So you'll see that when we do this. All right. Okay. Or a couple examples down. We'll walk through that. It's not hard. But you can always just let x equal t and y be f of t. All right. We are now up to line integrals. I'm going to kind of slowly break in. Are you ready? You don't have to write all this. Let me just kind of talk you through. Zach, you okay? Do you have a question before we move forward? Are you? Okay. All right. So, in the past, like last year, you knew that the integral from a to b of some function gives the area between the function and the x-axis, right? In two space. That's what we did last year. Okay. Then we learned in last chapter that when we do the double integral of some function of x and y, this would be like your z. If we do the double integral of z, where this produces the area of some region, we end up with the volume, right? Okay. So now we're going to have, instead of doing a dA over some region R, we're going to have C, which represents a curve, like the boundary of the region, and we're going to integrate over the arc length. So instead of doing the area and having like the area of the full region, instead, we're going to talk boundary and do arc length. So this gives you, I like to think of it, it's actually called a lateral surface area. I like to think of it as if you were to take the z function along this curve, right? So you get all these z values along this curve. If you hang a curtain from all the z values, it's the area of that curtain that's hanging down. So because you're taking all of your z values along that line and adding them together, right? Okay, so you end up getting this like funky area of a curtain that follows along some wire in space. Yes?
So it's just like a plane, it's not a shape?
It's not a plane. I mean, it can curve.
Okay.
Think of a curtain, if I took a wire and just strung it all over the place and then hung fabric from it, it would, like it's the area of all that fabric. It can curve this way, but yeah, it's still like a sheet.
Okay.
Yeah. Okay. All right. So anyway, the other thing that, now we're going to learn other things that it gives too, but it also gives the mass of a wire with a density of F. So if you just had the wire function, the C is that curve. So if you had a curve and you just had, instead of f of xy being a z value, say f of xy represented a density function, then you would have the mass of the wire. So, because again, you're just traveling along the wire with a thickness, right? Okay. All right. So, here's the fun part. So, this looks scarier than it is. All right? So, here's the definition of a line integral in 2 dimensions and the definition of a line integral in 3 dimensions. So we say that we're integrating over some curve C. Think of C standing for curve. So it's called a line. I wish they were called line integrals because it's not like these are straight lines. When they say line integral, they really should say curve integral, right? Because it could represent anything. It doesn't have to be straight. So anyway, so over some curve is the integral from a to b, this is like your lower t value, your upper t value, of your function, now written in parametric form, times the arc length. So in case you've forgotten, we did arc length in a different format let's see, did we do arc length last unit? We did, didn't we? I think we did. We did surface area. I don't remember. Anyway, so you know when you guys learned this last year, we did distance traveled in parametric form, and we talked about how it was the integral of the speed, basically, which is the square root of x prime squared plus y prime squared. So same kind of thing here. So this is your arc length formula. So a line integral, the integral from starting t to ending t, you just rewrite your function in parametric form times x prime of t squared plus y, square root of x prime of t squared plus y prime of t squared. If it's a three-dimensional function, it's the exact same thing, but with z's. Bless you. clinking. All right, we're going to walk through this one together. So this is our very first line integral. So we're going to integrate over the curve C of x squared minus y plus 3z ds. Remember, s is like what we use for arc length. All right, so C is the line that you're integrating over. In this case, C is a line starting at 0, 0 and ending at 1, 2, 1. So the first thing that you need is you need your curve, your C, in parametric form. So I want you to take a minute and do what you just did like 3 times and find the equation in parametric form of the line that starts at 0, 0 and ends at 1, 2, 1. Once you get your equation, I want you to see if you can find your restriction on your t values. What t do you need to plug in to start at 0, 0, 0 and end at 1, 2, 1? All right, let's see how we're doing. Good. You're already done. You guys are all done. Okay. All right, once you get your setup, go ahead and evaluate. You can clean this up first before you evaluate if you want. Bruce, are you done? You got 5, 6, 7. Oh, you got multiple things. Oh, that's not your final answer. This minus this plus this. Are you good? Okay. All right, we're moving forward. So I ended with, if you clean it up and combine the terms, I got 5, 6, and 6. Okay. Good, good. Nathan, are you okay?
Oh, yeah.
Okay. Are we good? Yeah? Good. All right. So we're going to take it up a little notch. And we're going to parameterize C. This would be a smooth piecewise curve. So from here to here, nice turn. Zach, really? Close it up. All right. From here to here, we have a line. From here to here, we're following a curve. Even though there are kind of some sharp turns, as long as this is smooth and this is smooth, then it's considered piecewise smooth. So we just kind of put them together. So we have one line integral for C sub 1 and then a separate line integral for C sub 2. All right? So your first job is to write C sub 1 and C sub 2 in parametric form. C sub 2, y equals x squared, is really easy if you just replace a letter with t, right? And then do something with it. Anyway, so you're going to, when you do that, when you write in parametric form, but the part that gets tricky is figuring out how to make it start at 1, 1 and end at 0, 0. So you might have to manipulate your function. So I don't know if you guys remember us having to like shift and subtract in order to make something switch around. Nathan, stop crying. It's okay. So your C sub 1 is really simple. It's just the vector t, x equals t, y equals t from 0 to 1. That everybody should have gotten without too much trouble, right? The problem with C sub 2 is, so we get t squared, except we're going 1 to 0, right? Which mathematically it's still I'm not even going to tell you it's going to work. So pretend it doesn't work. All right. So instead, whenever you have to reverse a direction, you want to make your t negative, right? So what I was doing over there was showing them if we changed c sub 2 to be negative t and then negative t squared, then what would happen is, what do we have to plug in to get 1? Our original t would be negative 1. And then what do we have to plug in to get 0? We would get 0. And this would be fine. You can do an interval from negative 1 to 0. But I went ahead and shifted everything to the right one more place just so I could start from 0 instead of starting from negative 1. So I let, instead of using negative t and negative t squared, I let it be 1 minus t and 1 minus t squared so that it went from 0 to 1. So that was, it doesn't matter. As long as it's mathematically correct. All right, so we've got our c sub 1 and our c sub 2. Now we're ready to evaluate this integral. So the first line integral that we're going to do is the integral over c sub 1 for t equals 0 to 1. So our t's are going to go 0 to 1. And then we have to rewrite our function, but for this one, x is just t. And then you have to multiply by the arc length. So the square root of x prime squared plus y prime squared. See if you can set that one up. And then see if you can set up this second integral for c sub 2. Again, for whatever function you came up with. See what you get. Are we starting to feel a little better about parameterizing? A little better? Okay. I'm going to skip this for a minute. This is just another line integral. It's already given a lot of your homework problems. They're already going to give it to you in parametric form. So, quiet please. If they call the function r of t, that's r of t, if you remember back to chapter 13, all of the paths that we traveled on were called r of t. And then if you remember, we did velocity was our r prime. Anyway. All right, so our r of t is like the path, so that's kind of like your c that you're traveling on from 0 to 6 pi. And remember that the line integral of the density gives you the mass of the wire, right? Okay. All right, so moving on. All right, this is the part where there's a lot of words, and I want to walk you through, and then I have a little visual, and then we'll call it a day, and we'll pick this up on Monday and do some more. All right, so one of the biggest applications of line integrals is calculating the work done on an object moving through a vector field. So we've been graphing vector fields. Now we're going to talk about an object following a path through a vector field and the work that is done on the object as it follows along the path through the vector field. Are you okay? You looked like you had a comment. Good? Vikram, you're good? Okay, good. All right. So suppose you have a force field, a field of forces, right? And we call it F. And you have an object moving through that field along path C. To determine the work done by the force, you only need to consider the part of the force that is acting in the same direction as in which the object is moving. So what ends up happening is you end up considering the dot product of F times T. Now, are we ready for a blast from the past? T is the unit tangent vector. In case you forgot, T is r prime over the magnitude of r prime, right? I told you it was coming back, and here it is, right? Okay, so and I'm going to say a little note, and then I have a visual. So note that when the vector field helps the object, kind of is pulling the object in the direction it wants to go, the work is positive. And when the vector field is pulling in a direction that's opposite the path that the object is taking, the work ends up being negative. And so I found this site, it's really cute. I use this site from time to time. So they've got this really nice visual. So this green kind of plane right here, think of that as like a gravitational field that's pulling towards the green plane. So this green vector, that's the direction of your vector field, your force field, okay? Now, this purple vector, that's t. So that's the vector that's tangent to the curve in the direction of motion of the object, right? So what ends up happening is when these two vectors are perpendicular, the work done is 0 because the dot product is 0. There's no work being done on the object. When it's moving, oh, by the way, this is your F dot T. There's your work right here, right? Okay. So when they are moving in the same direction, when the gravity is pulling the object in the direction it wants to go, you have a positive work. But then, as it moves this way, now the force field pulling this way, but the object's moving this way, and we end up having this negative work, right? So it kind of, as it spirals along, which I think is kind of fun to watch. I could like do this all day. Anyway, as it spirals along, you can see your work values change. Positive when it's going towards the force field, negative when it's pulling away from the force field, right? But this is what we're going to be studying is the work done on some object moving through along a path through a force field. All right. So I personally, just so you know what I like to think of this as, I think of the path as like a wire, and I think of the object as like a bead. Have you ever been a little kid and you played with those toys where you had a bead that could only follow along a wire, right?
No way.
Yeah.
No way.
Right. So that's what I think of when I think of these objects moving along a path, right? Except now you have a gravitational field pulling on it too. So anyway. Okay.
That's crazy.
So I have, this is just some visuals, but I actually have a really cute thing that's going to help derive something. So we have this, so to find the total work done, it's the line integral of the work. So we have the dot product F and T times the length of the path, which is that magnitude of R prime. So what happens is, since t is r prime over the magnitude, and we're multiplying by the magnitudes cancel, and you end up with this line integral just equaling f dot r prime. And it ends up making the integrals actually a little bit easier. So we'll start off with this on Monday, but here's my favorite part. So it's really f dot r prime dt. But I always like to, and this is really supposed to be kind of a dot, but I like to think of it as FDR, right? So I don't know if that makes, but it helps me remember it, right? Do you ever say FDR? Yeah, right? So anyway, okay, we're going to close there. You will not be able to do all of your homework, but you'll be able to do some of your homework, right? So get some of it done, and then what we can't do, we will continue with on Monday.